Good afternoon, everyone. I'm Gary Teague. I'm standing in for Sarah Hannock, who's not available today. I'm the affiliated organisation rep for SRP and member of council. Today's webinar is an introduction to contamination control. The ground rules for today, the webinar will be recorded and added to our YouTube channel shortly after this has taken place. The PowerPoint presentations will be made available after this webinar. Questions will be asked at the end of the presentation, so please ask questions through the Q&A box in the top corner of the screen. If there's a lot of questions today, the most liked will be answered, so please remember to like questions that you'd like to see answered at the end of the webinar. Please email the code on the screen and email to Tegan that's on the screen now, the email address, to register your attendance, and you'll receive an email with your 1 CPD point. At the end, can you please send your feedback? It's very important to us. We'll email you an online survey link for this after the webinar. Our very successful Radiation Protection Today magazine is available on the website. Issue 4 can be seen immediately today, and that's been on for several months now. The exciting issue 5 will be released this summer, which will feature the 60th anniversary of the SRP and sort of news about the big annual conference that we had in Aberdeen. A plug for the membership. Please visit the SRP UK website to join the SRP. There's so many great opportunities there. By joining the SRP, you can gain a professional status, you can get access to jobs, access to careers, all updates on future events, etc. So please take a look. I'm now going to hand over to Professor Pete Cole, our past SRP president and the current AURP president. Thank you.
Thank you, Gary. I hope everybody can hear me properly. It's my pleasure today to welcome our speaker, but just before I do that, I'd just like to remind everybody that the AURPL will have their annual scientific conference this year in early September in the University of Sussex near Brighton. We've got a great scientific programme organised and a great social programme organised, and I hope that most of you aren't afraid of heights. So without further ado, I'd like to introduce today's speaker. It's a pleasure to do this. John Bradshaw, a friend of mine. John is one of the RPAs working at AWE and is currently working as the radiation protection lead on AWE's new build projects, providing input as the RP intelligent customer. John has 30 years experience as a health physicist and RPA at UKAEA, Harwell and AWE Aldermaston, and is also a member of the RWA body. He occasionally supports AWE's internal regulation function, for example, as a peer review of the site's safety cases for AWE A and AWA B. He's contributed to the IRPCG guidance documents, either writing or commenting, and has spoken at the Cambridge Summer School on decommissioning and waste management. He's standing down as chair of the SRP Events Committee after many years of great service. And in 2020, he received the award of Honorary Fellow from SRP. So John's going to talk to us today about contamination control. And over to you, John.
Thank you. Right, let's see if I can get this to share. Whoops. Oh, no, got this wrong already. Right, let's click the wrong one. Right, here we go. Right, can everybody see that?
Yes, you're good, John.
Right, okay. When I was first writing this, I was reminded that, if you like, I've got to try and do this for all things to all people. So it's basically an introduction for example, if you're starting to go from the beginning, reviewing your current arrangements, think about decommissioning. So what I'm trying to do is, if you like, start at the beginning. There are some things that I did take out. I was actually going to talk about, for example, a bit about tritium. But one of the things myself and a few other people like Jim Bishop up at Sellafield, Jen Barnes, Gary Jackson Burton, is we're working up, if you like, a series of a bit more practical webinars for, if you like, people who are a bit more technical, that we're going to try and run with Sarah permission and Pete's permissions, so we can, you know, expand the, if you like, the depth of knowledge that we can share. So I'm going to talk about a brief history of, if you like, how we got here in terms of the legislation that and the improvements that we've made over the years. Some things to think about in terms of contamination control, and some tools of the trade that you need to consider as part of a LARP, as part of BAT, and having done your radiation risk assessments, all the things that you know chain up together to give yourself an holistic contamination control solution. So when I was thinking about this, I was going to start off with the cliche "Once upon a time in a galaxy far, far away." But was minded the fact that there's a song by Mike and the Mechanics called "The Living Years," and it says every generation blames the one before. And there's a lot of things where in the past we did, you know, contamination was tolerated out in the open. You know, and it was only until 1968 when we had the unsealed sources regulations that came along, we started to think about this, and these regulations were brought in through the Factories Act and didn't really apply to the nuclear licensed sites. Now, one of the things that brought it home to people like AWE, for example, was the poaching report, where due to bad standards in the buildings, people were getting very, very large intakes of radioactive material. So Cerebral Poaching did the report and hammered home the requirements to actually, you know, demonstrate contamination control, demonstrate things like a LARP, you know, and have dedicated health physics surveyors to do on the job contamination control to make sure people didn't get intakes. So as you're probably aware, 1977, there was ICRP 26 recommendations that basically says we are not going to do something called maximum permissible air concentrations anymore. You're going to do something called a LARP. And when the 1985 regulations came along, there were still things like, for example, you could designate your area based on airborne contamination levels, surface contamination levels for controlled areas. Now, in the nuclear industry, we've always used variants based around 0.4 becks per centimetre squared and the 4 becks per centimetre squared beta. Basically, we just carried on using the unsealed sources regs and just turned around and said, right, for example, the maximum limit on contamination will be 10 times those numbers. Obviously, I've missed out tritium because that was 40 becquerels per centimetre squared, because the people have lots and lots of fun with tritium. So the current regulations, you start off with radiation assessment, but basically says identify the magnitude of the hazard, think about what goes wrong if something goes wrong, you know, how you're going to eliminate, reduce, etc., and make sure all the staff are actually trained to restrict their exposure. So nice simple one to start off with. Regulation 9, the LARP regulation, so that basically puts the framework in place that says please start using engineering controls, please use procedural controls. It links into regulation 19 later on, which basically says, you know, if you've got a contamination controlled area, so far as really practicable, take steps to make sure contamination doesn't get spread everywhere, particularly going outside into things like corridors, etc. Now, if you work on a nuclear licensed site, that's almost a parallel with something called License Condition 34, which basically says if you've identified in your safety case, you can actually cock up and release contamination. basically, so far as we're practical, limit the extent. And if it does get out, make sure you can do some monitoring to demonstrate, how much has got out. Now, one of the things to think about is if you like the radiation safety culture, is if you can keep your area as clean as possible, not only, do people not like having intakes anymore, people don't like having loose contamination, it also makes waste minimization and BAT easier. So if you don't have the problem to start off with, your controls for BAT and, throwing stuff out at the end of the day are a lot easier. So let's start off with radiation risk assessments. So, if you're planning on reviewing any activity, so if you're starting afresh, if you're going to rekit, if you're going to do all these good things about updating, if you're going to decommission, it's a good place to start off with, to start coming up with some ideas. But what I suggest you do is do the first draft and stop. For the simple reason, you're going to have to start talking to a lot of people. So one of the things you've got to think about is, right, how are you going to do this? Developing a lot BATs and your radiation risk assessments, or a safety case, or whatever you want to call it, in lockstep. So that if you change one thing, review something else, it's all a holistic approach. And more importantly, it doesn't sit on the shelf. So if you like, it's not something that you tick in the box to get through the next, regulatory hurdle. It's something that you use. It's a living document and it breathes. Now, one of the things to think about is at some point you might want to write all these ideas down into a design strategy. So talk to any engineers, your maintenance guys. If you've got health physics surveyors, talk to them about how they want to do it. Talk to the management, because at the end of the day, it's going to cost a lot of money. So you need everybody involved, as they call it, stakeholder engagement, but it's talking to everybody, walking the corridors and saying, right, how do you want to do this? So how are people going to work? Are we going to have shift patterns? If something does go wrong, what sorts of doses are you looking to restrict it down to? So for example, zero accident dose, so far as reasonably practicable, how are we limiting all the dose? Who's maintaining all your equipment? How's it being maintained? Are you going to go out there and borrow other people's relevant good practice standards? Capture them all into a strategy. More importantly, if things go wrong, how are you going to decontaminate these people? So think about the personal care that you've got to put in place for these people who are potentially going to get contaminated, who are potentially going to have intakes. So what the follow-up bioassay regimes are going to be doing. Last but not least is instrumentation, which is another thing entirely. Pete Burgess, etc., have probably done talks at conferences. They've done webinars on this. I suggest you have a look at those, or talk to Pete, Mike Renouf, etc. John Littleford, Steve Damone. They can all give you help and advice on what instrumentation that you need. Oh, and Gary Teague as well. Not forgetting Gary. So, as part of the risk assessment consideration is what's going to happen if you start playing around with contamination. So what's the physical form looking like? Is it a solid, liquid, or gas? Is it going to go volatile? Is it going to change state? Is it like tritium? Is it going to go from, nice friendly gas into, tritiated water? What happens if you're going to chop things up? What happens if you play around and grind things up? So you've got to think about the aerosol that's being generated. So if it does get out, there's multiple things to consider on following on. For example, how's the vent system going to deal with it? With the particulate size as well is, right, how's that going to interact with PPE, RPE? All these things you've got to start thinking about. The other thing is, if you're playing around with the chemistry, is, right, it's not just about the solubility class for the dose consequences, because ICRP 130 has added more categories in terms of things like what happens with nitrates, carbonates, etc., etc. It's all about, things, for example, how are you going to dispose of the waste afterwards? Are you using acids or alkalis in your processing? So, these things damage containment. So you're going to need surface finishes to prevent degradation and things like this. Because at some point you're going to have to do through life refurbishment. You're going to have to refurbish everything. So the longer you don't have to do that, the better you can be. You've also got to think about, well, okay, at some point we're going to have to throw these liquids down the drains. So you've got to consider about pH for disposal, how much you can dispose. Are you using organic chemicals like toluene, you know, all these other things and all the other chemicals that you're using, because you've got to fix it into the waste route. But more importantly, if you have a spill, it is going to react with whatever the surface it comes into contact with. So that might make decontamination harder. So if you're thinking about a design standard and these things also apply to, if you like, going forward doing decommissioning, is what you really want is a decontaminable surface. The other thing to think about with decontaminable surfaces is, if you like, how are you going to clean them? Are you going to use something that we use, like, for example, rapid alcohol, which is a weak solution of alcohol in water? You could use Silit Bang. We've used Silit Bang for decontamination. But it's that thing of, well, okay, a sec. If I'm going to decontaminate it, is the decontaminating thing I'm going to use going to degrade the surface? So have a think about that. Cleanliness standard. Keep the area clean. Do housekeeping, because dust loads hiding behind things and bits and pieces. As I said, think about chemical resistant surfaces, because if you have a spill, it's going to interact. Curved surfaces are great for preventing accumulation of radioactive materials and things like corners. Electrical services and plumbing. Some people like, some architects and designers like having them open so you can see them and maintain them. As an RPA, I can't like them boxed in to prevent contamination ingress, because then it's easy to monitor in the event of a spill. And if you design it properly, you can actually, have these things where you can actually slide things off so you can get in and maintain them if there's a fault, inspect them, whatever. It's not difficult. It's just working with the engineers to say, look, as far as we're concerned, I don't want contamination traps. The other thing to take into account as part of your holistic risk assessment is working with a general health and safety advisor about non-slip surfaces and all the other hazards that you're dealing with, like COSH, biohazards, etc., etc. Again, to get that overall holistic solution to how you're going to do things. Just have a quick drink. So, as part of the BAT, you're going to be installing things to control the contamination spread to prevent, if you like, doses to the public. So, you get your vent system might have some filtration. You might have a stack sampler. So all these things have got to be considered. Liquid disposal routes. If you're going to have tanks, where's it going to connect to? Is it going to go to the public sewer? You need authorization from the Environment Agency. You need to think about, well, hold on a sec, if I'm going to put all these chemicals in there, is it going to make a mess of my tank system? Think about those sorts of things. We go through a lot of PPE, we go through a lot of PVC. Think about how you're going to assay all this equipment waste. How's it going to get moved around? How are you going to pack it? How are you going to repack it? More importantly, if you've got all these systems in place, they need to be inspected. They need to, tested. They need to be maintained. So all these things at some point are going to have to be looked at, fixed, maintained, repaired, etc. And you're going to have some sort of monitoring regime to keep an eye on them. So if things are starting to go wrong, not just physically looking for contamination, but things like, walking around the plant, is it grinding, etc., etc. All these other considerations that you've got to take into account. So once you've done your risk assessment, think about the engineering controls that you need in place. But again, think about it holistically. So what are the other things that are going on, like COSH, manual handling? And if you're accumulating radioactive material in some of these systems, is there going to be potential for external dose? Because that will be another driver about a LARP. So, for example, think about your design standard, which is going to help you, design all these things out. Think about containment, any additional containment that you might need when you're processing radioactive material. Think about the ventilation. Think about simple things like, safe change HEPA filters. So you can actually take them out, put them back in, and the job's done within about half an hour. So all these things to think about is to make everybody's job life easier. Having done your engineering controls, then you've got to think about the procedural controls. So as well as your local rules, they're going to drive a lot of things, is think about your housekeeping. So how do you want this to work? Is somebody going to around tidy up at the end of the day? Are people going to have a hoovers, brooms, mops, etc.? How's this going to work? Because some things you may turn around and say, right, hang on, we don't really want people mopping up stuff. We want to do something a bit more controlled manner, but have a think about how you want to do it. And last but not least, what's the designation of the area? So having done all these other things in the risk assessment and the ACOP is go, okay, I think this is going to be a controlled area or a supervised area, based on the radiation assessment, based on all the other things that go with it. And last but not least, don't forget about the PPE. So you need an inspection regime. So if you're going to have all this PPE, is who's going to inspect it? Where's it going to be stored? Make sure it's stored in a location, for example, where it can't get contaminated, where it's easy to get out in the event of emergency. But here's a list of things that you might want to consider people wearing. So things like lab coats, spare coveralls for protected operations where you're going and changing stuff, beta dose eye spectacles, spectacles in general, because people these days, if you're working with chemicals, etc., need eye protection. Hats, multiple gloves, because people change gloves at regular intervals. Safety shoes. If you're going over in a designated area, you might want contact shoes. You might want steel toe contact shoes for some purposes. Again, all comes out of your risk assessment process. If you're doing a protected operation, if you've got a contamination incident, you might also want to consider use of things like overshoes, PVC oversuits, to make sure, when you're decontaminating somebody or when you clean up after a spill, all these things you can actually do. Lead aprons, how are they stored? Where are they going to be stored? Again, think about all these things when you're setting up your area. And last but not least, the dosimetry provision. So are these people going to be working on bioassay? Are they going to be wearing PASs, personal air samplers? If they're having personal air samplers, where are they going to be charged? Where are they going to get them from? How are they going to get changed? Who's changing at the end of the day? So all these things you've got to think about when you're setting up your, a designated area, when you're reviewing your current arrangements, when you're thinking about decommissioning. So in the likely event it goes wrong, one of the things to think about is getting ahead of the game to start off with. So check to make sure all the engineering controls are working that you think they are. Are all your standards still working as you think they are? So it's getting over into the barrier, carrying out RPA audits, working with your radio protection officers, RPSs, and sit down with them and go, right, are we still doing stuff that's correct? Having people do radiological surveys. So again, who's doing it? What instrumentation is doing? What training have they got? How are they doing it? What the air sample results telling you if you're having air sampling results. So it all ties into your radiation safety culture. How are these people working? Are they coming back to you with challenges? Part of radiation safety culture, it's, you want an open and honest environment where, if you like, people are building up the momentum to say, we want to do something different. We want to change things. We want to get on with doing stuff. But at the end of the day, it's still going to go wrong at some point. So if it does go wrong, think about how people are going to be managed in the event of an incident. So how are they going to get help? Is it a simple thing like calling on a radio, using a phone? Because at the end of the day, you don't want them wandering around the building. You want people to stay where they are, people to come to them, start decontaminating. So think about who's decontaminating, what are they decontaminating people with. So are we going to have showers? Are we going to have exfoliating wipes? Where's this going to be done? Is it going to be a change room barrier, a little area? And the other thing to think about is as part of the training and instruction, etc., is, you know, walk people through training exercise on how to decontaminate people. So at the end of the day, when it does, if it does happen for real, everybody knows what they're doing. Everybody's rehearsed, and that little bit of panic that people get is manageable. And at the end of the day, if something does goes wrong, you've also got to plan for the waste arisings, including things like, you know, biologically contaminated waste. So, for example, if somebody's cut themselves, you've got a blood-stained tissue, how are you going to dispose of that? Have you got the right permissions? So again, it's thinking in front of saying, right, if something does go wrong, have I got the right permissions to do what I need to do to help people? So as a starter for 10, there is a book that everybody calls Delacroix, which is basically the 2002 edition of the Radiation Protection Dosimetry, entitled Radionuclide and Radiation Protection Handbook 2002. So that's got a lot of information as a starters for 10 for things like activity limits and suggested controls for area designation. Now, you've got to bear in mind that, like I said, holistically, you might need to do something different. So, for example, your dose rate may require additional controls. So there's some examples of containment. So you've got a gentleman working with a fume cupboard, and you've got some people working in some glove boxes. So a fume cupboard is good when you're processing low levels of material. In the event of an incident or spread or whatever, it does reduce the contamination levels by a factor of 100. It can be better, depends on, you know, what your safety case and safety specialists have agreed on. But it does depend on good housekeeping for laminal flow. So, for example, if you've got a fume cupboard full of stuff, that is going to affect how it's going to behave. So you might get contamination blowing out. The other thing is, if you sited it near a door, the effects of opening the door, etc., might cause, again, disruptions in laminar flow, so it might not be doing its job as well as expected. With these sort of things, you can actually add in local shielding. So, for example, I'm involved with people who've been using iodine 131, phosphorus 32, technetium 99. We've worked with them and said, okay, if we do this, you might need some additional perspex shielding to reduce the dose as well. The next stage up is a thing that we all know and love called a glove box, which is very good pretension, but they can be more expensive to buy, maintain. If you want to make them out of stainless steel to reduce dose, they're very, very expensive opposed to a cheap one which is made out of perspex. Now, if you can still demonstrate this a lot, but don't forget they're still happily working on a bench where you've got small radioactive material, where you've got a nice ventilation, and you're working on stuff on a drip tray. So if you think about ventilation, which is giving you a help to prevent, you know, spreads of contamination, that's a typical drawing of a designated area from the old nuclear ventilation standard. So what you have is a change room, you have a lab area which has got a fume cupboard, it's got a glove box, it's got a cave area for maintaining, you know, working on high hazard material, and the aim is to have the airflow flow into high hazard areas. So, for example, you start here at the foot barrier. You want to try and keep your change room as clean as possible, because in the event of an incident, you want that to the first starting point where you're going back into your lab. So you might consider having an airlock where you go in. So when you go in, people are wearing whatever clothes you recommend, whatever PPE that you recommend. So, for example, they might be wearing coveralls, they might be wearing lab coats if it's that simple, if it's just a fume cupboard that you're working with. I should point out that these designation of areas are from that's something that the Ventilation Forum came up with, because everybody across the United Kingdom uses different standards for designation of area. They came up with a system where they said, okay, for engineering sakes, to keep that so they can understand what's going on, is they have a white area which is undesignated, a green area which is a supervised area, red areas, which are, if you like, controlled C4 areas, and then you've got an amber, which is a standard controlled area. So all these things that they try and build up, they're in a slightly different system of designation. So, for example, we would have a supervised area in the change room. This would be a controlled area, and depending on how you do designation of area, that might be what we used to call at AWE a purple area. We can't get in. So again, the name of the game is to make sure that the airflows are running in the right direction. So, for example, if there is a breach while you're working on the glove box, the airflow isn't going that way, it's going in towards your ventilation system. So the current ventilation standard for radioactive areas is this one at the top, ESO 1738-1. Now, one of the things to remember is that the risk assessment ALARP drives the ventilation requirements, not the designation of areas. Over the years, I've had a number of discussions with the vent engineers who've said, you've said this is a controlled area, we're having 5 air changes an hour. And it's like, well, no, is the risk assessment and the ALARP tells you what the ventilation should look like, not the designation of areas, because that's just, if you like, a tick in the box to go, yeah, because ALARP at the end of the day is going to tell you, well, actually, I might want more air changes. And like I said previously, it should flow from a low risk area to a high risk area, again, to prevent, contamination going where you don't want it to go. Now, these days, they usually do it by something called pressure differentials. So you use the pressure drops to make sure that the airflows are going in the right direction. And ideally, it should be from a high level plenum to a low level extract. So air comes in at a high point and extracted low, because in the event of a contamination release, because you know what the size of the aerosols are generally going to drop. So if you're using something like, I don't know, say, for example, uranium, that's fairly heavy, that's going to drop down. So that's going to get easily drawn out by low-level extracts. I've had actually a number of debates with engineers about whether or not it's high-level plenum, high-level extract, high-level, low-level, low-level. We can talk about that another time. But one of the things to think about is, as I mentioned with the drawing previously, is think about the fume cupboards, think about maintenance. So at some point, all this equipment is going to have to be maintained. So ideally, you want it in a place where you can actually maintain it easily. And again, holistically, ALARP BAT drives what your requirements are for a HEPA filter, your stack sampling, etc., etc. So you're going to want to speak to a ventilation engineer. Now, when I've talked to them, they've got a very practical approach to how ventilation systems work. So, for example, rather than using something like, some mathematical model to actually do stuff, it's better if you talk to them and go, okay, I've got this area, it's got a fume cupboard, it's got glove boxes, how's it going to work? So if I put all of these things in, where should I put the extract points? Where are the dead spots? How am I going to do my air sampling? Where's the best place to go air sampling? Now, one of the things to think about is the vent system. You don't want contamination being resuspended. So what you want is the optimized, minimized vent velocity, so that in there is an incident, it's not going to go bouncing around the room. Think about the number of air changes an hour, because the more air changes an hour is lower the doses. But one of the things that goes with that is if you've got more air changes an hour, the energy requirements go up. And, that affects, the lifetime of the equipment, how often you do maintenance, etc., etc. The other thing to think about is, because you've got a ventilation system, is what happens if it goes wrong. So how are people getting out? What's the contingency plan? So think about that as well when you're doing all these things. Maintenance. Again, as I said, work with a ventilation engineer about how often it's going to be maintained, where it's going to be maintained, can people maintain it? So, for example, try and insist that when you're rekitting, etc., is I can actually get access to that ventilation plant. Can I get access? Mainly because you can't really monitor above 6 foot up in the air. if people are having systems, up in the air that taller than 6 foot, it's going to be difficult to actually monitor the equipment. It's actually going to be difficult to maintain the thing if it's that height anyway. So it's working with them and saying, look, guys, I want something that's at a nice height. One of the advantages of having a ventilation system is this time of year, I'd rather be in a designated area than sat in an office because, I've got a nice environment to work into. It's nice and cold or nice and cool, even though I'm wearing a coverall, but it's great. Now, one of the things to think about is you're going to get condensation sometimes. So it's how you're going to clean that up. So again, it's another thing to think about is, well, I could get a rag and dry them out. Is that appropriate? Do I need to dry it out in a fume cupboard or whatever? And as I said, is once you've had a discussion with your ventilation engineers, you can understand, well, do I want one extract point for the room or do I want more extract points? Because how I'm doing this is going to determine how I'm going to do my air sample. Now, there is a technique called computational fluid dynamics, which people can actually use to look at ventilation patterns. If it's complicated, if you've got things like a furnace that are going to generate resuspension in the event of a lease, it can actually help with the modelling, but it can be very, very expensive as well. So as a first guess is always talk to a ventilation engineer about how you want it to work, how you need it to work. So if you do need additional controls, think about things like temporary ventilation controls, temporary ventilation enclosures, things like tents, modular containment systems. So a tent's quite straightforward. It can be put together on a Dexian frame. It's made out of PVC or polythene. It gives you a nice decontamination factor. So if there's a release, it's going to knock it down by somewhere between 100 or 1,000, depending, again, what your safety case approval looks like. And they're great for temporary jobs like, for example, maintenance. So if you're going to maintain a bit of kit, if you're going to change your HEPA filters, you might want to consider something like a tent. If you're going to step it up, or based on the risk assessment approach, so for example, if you're changing a window in a glove box, if you're actually decontaminating, if you're decommissioning a facility or a glove box, you might need something that modular containment system, which can be made out of a material called Modicon. Those are very robust. They're very fire retardant, and based on some numbers that we came up with at AWE, don't quote me, but it reduces the airborne concentration by a factor of about 1 million. So that's the difference between what's happening inside the containment to outside. Now, one of the things to think about is if you're bringing in some additional systems, is do you need some additional ventilation? So you might want to bring in a mobile filtration unit. However, that might have to be balanced with the current ventilation system, because I have actually seen mobile filtration systems brought in, and when they fired them up, they've unbalanced the vent system and they've actually sucked contamination out of fume cupboards and things like that. Ideally, you're relying on dynamic contamination for control, because when people are coming in and out of tunnels, the airflow in the tunnel is going to help you with decontamination, prevent the spread of contamination when people are coming out. Ideally, that's the sort of flow velocity you're looking for, somewhere between 0.7 and 1 meter per second. That's also going to mean, additional RPE, PPE requirements. So have a think about how they're changing. Are they changing before they go in? Are they wearing a pressurized suit? What PPE, what RPE are going to be using? All these other things you think about. Think about the monitoring. So when they come out, how are we going to monitor them? Are we going to monitor them in the tunnel? Are we going to monitor them as they come out? It's entirely up to you. Air sampling, and other forms of monitoring is, air sampling inside the modular containment system, inside your tent. Can we do that? What are we doing outside? Do I need to rig up some additional power cables to actually do it? So again, it's thinking about, well, if I need to do the monitoring, what's the infrastructure I need to make sure it happens? Now, ideally, as I've said, equipment should be designed so you can get at it, so it's easy to maintain. So if it does, is there a breakdown, it's easy to open it up and get at. So it's making sure you've got the space when you're setting up, if you like, your temporary area to start maintaining these equipments. Is have you got the space for the parts? Have I got the space for my health physics monitoring gear? Have I got space for air sampling? Have I got space for waste? Have I got space for PVC, etc.? So I can actually kit up the area, so I can actually prevent any spreads of contamination that might happen while I'm taking these things apart to maintain them. The other thing to think about is those engineering controls that you've got in place, you're now going to defeat while you're maintaining them. So what other things do I need to put in place? So for example, do I need an additional vent because I might be generating a confined space? I might have chemicals coming out all over the place. So do I need anything additional to help me do the job? Now, again, talk to your health physics surveyors, talk to your health physics monitors, talk to your RPSs. Some of the controls you can actually do are as simple as, okay, it's coveralls, respirator, lots of PVC and a tensor barrier to restrict access around to the area. But as the hazard steps up, you may want to consider additional controls, like, for example, bringing an MFU. You may need a tent, you may need a PVC, you might want to restrict the entire lab. All these things to think about when you're doing a breach of containment to try and fix the area. So having done a lot on the engineering controls, you need to think about procedural controls. So as well as all the good things from the IRRs, so things like no eating, drinking, smoking, taking snuff, applying cosmetics. Think about all the other things that you want to think about for how you're building, how your area is going to work. So are you going to have operators self-monitoring? So when they do an operation, they're working a fume cupboard, how they're going to have, training in how to use the monitors when they're monitoring themselves out. Are we going to have a housekeeping regime? When things go wrong, how are we going to deal with the problem? So if, for example, there's a fire alarm, if there's a contamination spill, how are we doing? And again, what's the survey schedule to pick up breakdowns in containment, breakdowns in failures, etc., etc.? Are we going to have air sampling? How's it going to look? PPE. One of the best sources of information is the HSG 53 on advice on RPE. It's a very good read. It gives you great advice on all the different issues to discuss when you're doing RPE selection. The other thing to consider, and as I mentioned earlier on, is your aerosol size. Think about PPE and the physical challenges that are involved. So if you're making people wear coveralls, if we're going to have a liquid spill, is it going to penetrate through? Is it an organic problem? Is it aqueous? What's the recommendation from the British Standard and the ISO on the PPE? The other thing to think about is all the compatibility and work environmental issues. So if you're going to put people in PPE, if they have to wear a respirator, do they need a bump hat? Because if they bang their head, that might be a bigger problem than the respirator. So is it a compatibility issue? Making sure you get a respirator that's compatible with a bump hat. If you're wearing a blouse, or an air hood, similar again, you might want to incorporate a bump hat or whatever as part of the design of your RPE. So if you've got a blouse or an air hood, if you do something like that work, consider that. If you're working at height, you might need a fall resting kit. Again, that's got to be compatible with the PPE that you're going to be using and the RPE. But all of these, think about the time of the year. Think about heat stress. There's some very good papers by the ONR, the Health and Safety Executive and the Health and Safety Laboratories on things like heat stress when you're wearing PPE, when you're wearing pressurized suits. So read those and take into account those when you're planning the job. For a simple reason, you might want to turn around and say, on a nice day like this, we work at 7:30 in the morning. Think about heat stress, because as you're wearing all this PPE, your internal body temperature climbs. So once you've finished the job, it may still be climbing. So you've got to step back and say, right, okay, now we've finished the job. Go and have a sit down, go and have a break. You might need longer than what you think. As the last slide, I've had a number of discussions with engineers over the years. One of the things that I've been invited to speak at is the IMECE conference. So one of the questions they've been asking me is, why do we do additional designation of areas? Why do we tolerate different values of loose contamination? Some of it is basically about a LARP, about safety culture, that we all do things differently. As it turns out, they've how can I put this? I always thought engineers were always, it was all this, that, and the other, and it's all done by a book. But everything, they've got the same things that most people have, when they're asking questions is, well, what does the aerosol do to the vent system? How does it affect it? Why do you treat alpha and beta emitters differently? Culture, for example, what you do for tritium might be different for plutonium. And again, what happens if things go wrong? So how do you, as an RPA, account for things like things going wrong in an incident? How does the contamination get removed in the event for post-incident? All these things to think about. So I was actually quite refreshed and surprised that these things are, they're a bit concerned about them as I am sometimes. Anyway, thank you very much.